we'll be talking also about chemistry, and yeah, I'm in charge, but also Vincent Weird, and so we are two co-leading the project. So yeah, we'll talk about what we do, the activities we hold in CAMS 235, about global chemistry and aerosol modeling aspects, mostly about plants, but also some first results. So what do we do in CAMS 235? I mean, basically, what we do is to try to improve the global aerosol and chemistry trace gases modeling aspects. So working on the IFS to try to improve processes, various parts. The ultimate aim is really to help ECMWF in providing better quality CAMS products. So we started in September 2021, so we already have a few results. So in detail, we try to design and we propose model upgrades to ECMWF for tropospheric and stratospheric chemistry and aerosols. We develop and evaluate possible new products, deposition fluxes, and others. Of course, there's a strong evaluation side to all of that, and so we acquire and we process a lot of observations to evaluate our model changes. And well, of course, we assist and we help ECMWF in implementing all of these changes and in building and evaluating new operational branches. So in detail, design and test proposed model upgrades. This is a list that is not exhaustive of what we have planned for like the next 3 years. So implementation of allergen chemistry in troposphere, that's work from Jason and Vincent and so on. That's a very large upgrade and that we will propose in sometime later. We will include actually a simple representation of stratospheric aerosols in the tropospheric IFS-IR scheme so that we can better represent the impact of large volcanic eruptions, better representation of aerosol acidity and its impact on many chemical processes, new aging parameterization, upgrade and optimization of the photolysis of stratospheric chemistry, which is quite a key task in terms of computing, again, a computing cost. A lot of work, of course, on desert dust, which is quite a key product from the aerosol side, asphericity, hydrophilic growth, etc. Upgrade of the heterogeneous chemistry, and especially the link with aerosol acidity, and some code optimization, and plenty of other tasks. So, of course, we can discuss that if you're interested in more detail. So I will show maybe in more detail some initial results we have on work on the better representation of aerosol acidity and code optimization. So aerosol acidity is something that we didn't take too much into account in the IFS beforehand. I'm showing here this plot taken from the Payetal 2020 literature review, which is showing basically the life cycle of aerosol with hydrophilic growth and then cloud as a CCN and then being deposited as precipitation, and the impact of cloud, so aerosol acidity on cloud acidity, then on precipitation acidity, and how it then actually impacts different chemistry reactions, especially aqueous chemistry, and also the scavenging of some trace gases. So what we did is actually to implement into the IFS thermodynamic model called EQSAM4CLIM that's been developed by Sven Metzger, who's part of the project, which basically uses input from both chemistry and aerosol, and also from the IFS and WP itself, and compute, so aerosol, sorry, my bad, and yeah, compute basically aerosol water, gas particle partitioning for nitrate, nitric acid, and ammonium and ammonia, and ambient pH. So what we use, that's what we use here in this work. And so we evaluated, output and archive and aerosol pH, cloud pH, and precipitation pH. And we've evaluated that against, well, routine observations or observations from different, let's say, field campaign. And here, this is actually for the rainwater pH. So I'm sorry, I think I've wrote cloud pH, that's wrong. That's precipitation pH as compared to observations, routine observations from CASTNet of the US, from EMAP of Europe, and from EANET in Asia. And also, again, some reference simulation done by Geoschem that's being described in detail in this publication, and showing that we're not doing too bad, at least at the continental scale, in terms of simulated precipitation pH. So that's quite encouraging for first results. And when we look in more detail, you can see that as compared to observations in circles, we have a Our simulated pH, okay, is not perfect. We are probably too high here in central US, but we clearly reproduce quite well the broad patterns, like with more acidic here on the eastern coast, on the western coast, and more alkaline in the center of US. Same over Europe. We miss some features, but we probably do manage to represent the big picture in terms of acidity of precipitations here. So the impact of this aerosol acidity work, and also in the implementation of EQSAM for Clim and optimizing actually the input, the output, and the processes in EQSAM for Clim on simulated aerosol species can be very positive. It's not positive for all species, but for some it's really striking. Here, this is, for example, surface nitrate, so aerosol species over compared against castnet observation. This is weekly data. I'm sorry, that's cropped here. That's bad. But basically, what we show is that we have a reference here in forecast only 48I1 for 2019, with, which is heavily biased. I mean, we have a very strong positive bias, and that is much better for bias for MSC and also for correlation. That's showing an example here for weekly simulated and observed nitrate at surface. So the black line, that's the observations at McVille in Kentucky, US. What we had before in 47R3 or 48R1 is shown in blue and green, and what we managed to get with these new developments is in red, so that's quite encouraging again. So we carried out also a review of computational cost for composition, so aerosol, chemistry, tropospheric, and stratospheric. So the chemistry module was found to be much more expensive than the aerosol module, which is well known. But in addition to just reviewing the code, we also suggested some improvements, and particularly in the implementation of the timers and the code that really helps to trace back errors. And that's work that was done by Vincent. And the results are shown here, where we can see actually the computational cost in system building units of the chemistry module and different components of the chemistry module, which is actually halved after, like, so divided by 2. After the implementation of the simple optimization procedures that we suggested. So this is now implemented in Cycle 48R1, and so that results in an overall decrease of 33% in the computing time of the whole model integration. So that's a that's a very nice result. Moving on to actually future new products, so not anymore model development, we plan actually to assist in proposing these new deposition products, global nitrogen, sulfur, and dust deposition. And of course, before doing that, proposing that to the general public, we clearly need to carry out some thorough evaluation. So this is activities that are planned in the future. We didn't start working that much on it yet, but we're already looking at the simulated, for example, wet deposition of sulfur, so here SO2 plus SO4, as compared to observations in circles. So this is over US, over Europe, and over Asia. So it seems that in forecast only, we are probably on the high side of the US, maybe a little bit on the low side over most of Europe, and, well, a bit of both over Asia. So that's a very initial assessment, but we start working on these aspects as well. In terms of dust deposition, again, there's not that many observations available for dust deposition, but this is showing actually some product that's provided by Hongbing Yu from NASA, who kindly provided the data, as compared to simulated dust deposition, dry and wet, from IFS lower down. That's not purely comparable because I'm showing here like an average over 10 years, and this is only like a 3 average, but that's showing that our simulated dust deposition is at least not too bad as compared to this product. So that's very initial, of course, and we'll carry on this task later in CAMS 235. About the acquisition of observations and for evaluation, so we've acquired and we plan to acquire a lot of observational data sets. I mean, we have several dozens of them and counting. And we gather that in a living document which we share with SMDF. So an example here is actually how we use those observations for evaluation. That's from Jason's paper, which is soon going to be published in the GMD. It's been accepted, and showing actually a variety of aircraft campaigns: top-down, Discover IQ, Frappy, Winter, Songnex, and showing how we apply them for NO2 profiles evaluation for different periods of time in the summer 2014 and winter 2015, and also showing a comparison of the chemistry analysis profiles and the three tropospheric chemistry schemes that we are maintaining in the project. So of course, I won't go into too much details of all of that, but that's just an example of how we use observations for evaluation purposes. We also actually maintain and develop two evaluation tools and many scripts and smaller scale software, of course. Eval tools and GDF eval. So eval tool was presented in more detail by Mehdi yesterday. This plot is showing, for example, an example of ensemble skill scores produced by eval tool, distribution, Talleyrand rank histogram, and some quantile time series. In terms of operational support to ECMDREF, so that's, there's been a lot of work in helping ECMDREF in setting up, evaluating, and testing the cycle, next cycle 48R1. So the big upgrade, of course, as Jonas mentioned, is the use of BASCOE for statistics chemistry. So that's a few more plots here showing, for example, the positive impact of using CB05 BASCOE as compared to CB05 alone, compared to reference dataset, MIPAS BASCOE, like reanalysis. And yeah, again, I'm not going to go through all of that, but clearly the impact, if you compare the blue line, the new one, as compared to the red one, which is the current situation, as compared to the black profiles, that's positive for most of the species of interest. The other upgrades, I think Jonas detailed them, but that's, there's been some large regions of tropospheric chemistry. There's the new secondary organic aerosol species. That's quite an important change as well. Sectoral emissions instead of bulk emissions. I mean, that's a very, again, a very large-scale change, and some dust upgrades, which we discussed with Marion yesterday. So to conclude, I mean, that the CAMS 245 started well, and there's been a very smooth transition from the predecessor projects, CAMS 42 dedicated to chemistry, and CAMS 43 dedicated to aerosol global modeling. We're already working on the next cycle, so on cycle 49R1. And clearly the developments, they all go in a direction of further integrating aerosol and chemistry aspects. I mean, we can't really say anymore that there's an aerosol component and a chemistry component, and there's a bit of both on both sides. And yeah, as usual, for any question, I mean, you can come to me or to Vincent. We'll be happy to answer you.
Thank you. Thank you very much, Samuel. Questions? Let me check it. Okay. There is one question from Richard Engelen. For you or for Johannes, I don't know, are the optimization results represented by SAM already included in the graph from Johannes?
Well, I think it's more for Johannes to answer, but I think they are.
They are included to a large extent, especially what was mentioned, that the timing function itself are very costly. This major kind of bug also has been removed. Yeah.
Okay. Thank you.